Yeah, please.
Go ahead.
It's my great pleasure to have Professor Kim Stelson, who is the founding director of the NSF Engineering Research Center for Compact and Efficient Fluid Power. He is College of Science and Engineering Distinguished Professor Emeritus in the Department of Mechanical Engineering at the University of Minnesota, where he has been since 1981. His research includes controls and fluid power technology aimed at improving efficiency of off-road vehicles and wind turbines. He has received the Rudolf Karlman Best Paper Award from ASME twice, a fellow of AAAS and ASME, and has received the Koski model from ASME and the Brahma model from IMECHE. Today, he will be talking about energy-saving fluid power technology for off-road vehicles. And, off-road vehicles are all over the place in construction, agriculture, forestry, and especially in the context of India, where a lot of development is going on. I believe these vehicles play a very important role. With that, I will hand over the mic to Professor Stelson to start the lecture.
Oh, thank you very much. It's my pleasure to be here today. Good morning or good evening, depending on where you're at. Let me start the screen share here. There we are.
Yes,
okay.
Thank you.
All right,
Very
there we have it. Okay, so the topic is energy-saving fluid power technology for off-road vehicles. This is an updated version of a talk I gave in September 2024, but there have been a lot of changes in the government in the United States. And rather than editing it, which would disguise the changes, I've added comments in red, so they'll highlight those changes. So let's start with some basics. Humans have caused climate change, and humans have the agency to slow or reverse climate change. Those are simple facts, irrefutable facts, even though many people, because of certain special interests, deny them. And climate activists use many words to disguise the reality of climate change. I have this is from a book by Michael Mann, some of these words. I'm going to focus on the three here: denialism, deflectionism, and doomism. So denialism is to simply say that climate change doesn't exist. Of course, this is not true. It's a hardy perennial, though. We just don't seem to get rid of it because it's in the self-interest of people to deny climate change. The other extreme is doomism. Doomism is the idea that climate change is here and it's inevitable. It's so bad, we can't really do anything about it, so we might as well enjoy life in the meantime. That's doomism. And a more subtle thing is deflectionism. And deflectionism is the idea that climate change exists, but it has to do with who's responsible for it. One idea that sounds good at first, but is really insidious, is the idea of an individual carbon footprint for each person. And it's fine to calculate that, but it promotes the idea that solving the climate crisis is an individual responsibility, and it lets the fossil fuel industry off the hook when it's obviously a societal responsibility and requires collaboration. Individuals simply don't have the agency to solve it. These are a few cartoons from Tom Tolles. He wrote a book with Michael Mann a few years ago. Sadly, these cartoons are still relevant, even though they're a few years old. We see two frogs here in a pot of boiling water, and one frog says 2014 was the hottest on record, and the other frog says stovetop temperatures change all the time. So that's denialism. And here's another cartoon from Tom Tolles showing that it's always too early to do anything about climate change until it's too late. So it sort of combines denialism and doomism in a single cartoon. But now let's talk a little bit more seriously about the talk. We are talking about transportation. And to put this in context, global warming is generally caused by 4 different areas, and they're roughly equal in their importance. And these areas are electricity generation, transportation, manufacturing, and everything else. And so if you focus for the moment on transportation, transportation consists of light duty and heavy duty vehicles. Light duty vehicles means passenger cars and light trucks and the like. They make up about half of the transportation energy and the emissions. Now, in the oil shocks in the 1970s, we got a wake-up call for light-duty vehicles. And in the decades since, we have improved their efficiency by about a factor of 4. So it's been quite a dramatic reduction in fuel consumption for automobiles. In contrast, the different areas that I'm showing you here, aviation, naval applications, rail, and off-road vehicles, have only modestly improved. And because of that, they're becoming increasingly important in the transportation sector. And we can do things about these different sectors to improve their efficiency, mainly because there's been so little done to date. So here shows, this is government data from, it's a little bit old data. It's from 2009, but there hasn't been this kind of exhaustive study done since then, but the situation hasn't changed very much. So heavy duty vehicles, or what for some reason I don't understand, the Department of Energy calls them non-light duty vehicles, consume, as I said, about half of the energy in the transportation sector. And this is measured in US government reports in a unit called a quad, which is a quadruple, quadrillion rather, BTUs, which is a very bizarre unit. But happily, one quad is almost 1%, almost exactly, of the energy use in the United States. So we can interpret these numbers as percentages. So in the non-light duty vehicle sector, the largest consumer, as you can see from this graph, are heavy duty trucks. But off-road vehicles are roughly half of that. And off-road vehicles consume more energy than aviation, more than marine applications. It's very important. It's about 8% of total transportation energy. And let me just explain what it is. Off-road vehicles are vehicles that are used for construction, agriculture, forestry, and mining. Okay, now one of the reasons or the challenges people state for improving the technology in this sector is the great diversity of vehicles. That's true, but if you do a study, and actually our center actually commissioned this study to find out what the distribution of vehicles are, you can see that most of the fuel goes into, in the construction area, goes into 2 different machines, wheel loaders and excavators. So if you can improve the efficiency of these 2 machines, you can greatly improve the overall sector. Moreover, the architectures of these different machines are actually very similar. In fact, wheel loaders and excavators don't vary that much. Let me show you what they look like. I'm sure you've seen these machines on construction sites, and they they are very inefficient. For example, about 40% of the energy in an excavator is dissipated in the valves, which is used to control it. So there's a large opportunity for fuel savings in these machines. Uh, and we can do this, and I'll explain it in more detail later, by four means: efficient engine operation, hybridization, throttling elimination, and closed loop control. So if we could realize all of those improvements, we could take the average energy efficiency, which is currently 30%, and increase it to 40%. The optimal efficiency of a diesel engine is somewhere between 40 and 45%. So you get closer to optimal. By getting rid of the valves and other things, we could improve the system efficiency, the transmission system efficiency from 40% to 60%, which would mean that the overall efficiency would increase from 12 to 24%. And that would save us 1.2 quads, or more than 1% of all the energy consumed in the United States. Okay, so I'm illustrating these ideas on this figure. The upper right-hand corner has what's called an engine map. It's a map of torque and speed for an engine, and with contours of constant efficiency. And you see an optimal operating point there, which is about, in this particular case, I think it's about 42% efficiency. And so that means we must keep the engine near that point to be efficient. And that point is at a moderate speed and heavily loaded. And unfortunately, in most of the operations, first of all, that operating point wanders all over the place during the operation, but it tends to be at higher speeds and lower torques, and for that reason, less efficient. Now, if we're going to keep the operating point of the engine near the optimum, we have to have a way of storing and releasing energy. Otherwise, the instantaneous torque of the load has to match the engine torque. So we need to hybridize, and this hybridization is generally done with hydraulic accumulators. And that's the most important advantage of hybridization, is to keep the engine near its most efficient operating point. But in addition to that, we can recover energy during certain phases of operation and reuse it, which is an additional benefit. So energy recovery is shown in the upper left-hand corner. Now the lower left-hand corner is a picture of the throttling valves, which are used to control the various circuits. So unlike an on-road vehicle, where the primary energy consumer is just propulsion, everything else is very small. In these working vehicles, we have separate circuits for doing work in addition to moving the vehicle along. So these various circuits are then powered by a single pump. And the challenge here is that different circuits within the machine require different pressures. But the pressure that the pump produces is determined by the maximum pressure. And for those axes that require much less pressure, a significant amount of energy is dissipated as heat through throttling valves. So if we're ever going to make these machines more efficient, we have to eliminate the throttling valves and control it in another way. And then the lower right-hand quadrant shows the fact that these kinds of controls we're talking about are not simple, and they require sensors and actuators and closed-loop control, and that's another essential element. So to summarize, we need energy management, energy recovery, the elimination of throttling valves, and intelligent controls to improve the efficiencies of these machines. Okay, so here's where we are today. As I said, off-road vehicles consume about 2.4% of U.S. energy, and it's possible to reduce this energy by half to about 1.2% with realizable technology. And beginning in 2018, the U.S. Department of Energy invested, or since then, $37 million in R&D to realize this reduction. And this program, by the way, was the result of intensive lobbying during the period of 2016 to 2018 to realize this. So we've been doing a lot of these projects with this funding. This has been through an office in the Department of Energy, which is called EERE, or Energy Efficiency and Renewable Energy. And in 2025, the name was changed to the Office of Critical Minerals and Energy Innovation to downplay the role of energy efficiency and renewable energy. The government has been accused of cutting this research off. They deny it, but it's really undeniable what's going on here. Okay, here are some of the results of projects funded by this program. And there have been many projects, but I'm going to restrict myself to those that my colleagues and I have done at the University of Minnesota. So one way to improve the efficiency of these machines is through more efficient components. And my colleague, Professor Vandeven, developed a variable displacement linkage motor, which proves to be more efficient than a typical swash plate motor. And also, the variable displacement aspect is generally not used on track loaders, such as this one shown here. So by having the combination of a variable displacement pump and a variable displacement motor, we can keep both the pump and the motor in a more efficient operating area, and this could actually reduce fuel consumption on this machine by 30%. So that's an example where by improving a component, we can improve overall efficiency. This is generally not how it's done. The bigger advantages come from changing the system configuration. And here's an example of changing the system configuration. Now, as I mentioned, there are many different actuators, cylinders and hydraulic motors and so on an excavator or other similar piece of equipment, and they are all powered now by a single pump. And the problem is, as I mentioned before, these different axes require different pressures, and because the pressure provided by the pump is dictated by the highest pressure needed, all those circuits with lower pressures are very inefficient. So we have to get around this some way. And one way is through the use of pressure rails. So if instead of having just one pressure available, we have multiple pressures, the different axes can choose the pressure differences that are most appropriate for what they need. That would be a pressure difference which is greater than what they need, but by the smallest amount. So for example, if we had a certain supply pressure and we had the tank pressure, which is at atmospheric pressure, and we had another pressure available which was 1/3, let's say, of the supply pressure, we could get pressure differences of 1/3 of the supply pressure, 2/3 of the supply pressure, or the entire supply pressure by choosing to use these different pressure rails. Now, this idea was first demonstrated at the Technical University in Aachen some years ago on a Volvo excavator, and they validated the concept and showed significant energy savings. Now, what you're looking at here is from my colleague, Professor Perry Lee, who has taken this one step further. Instead of having picking the largest pressure or the pressure difference that just exceeds the required pressure by the smallest amount and throttling the difference, Professor Lee's approach allows the system to select the pressure difference which is nearest what is needed, It could be a little bit higher or it could be a little bit lower. And then electrically making up for that difference by boosting and bucking, and then storing or releasing energy from an onboard battery. And this shows this configuration. And this approach causes significant energy savings, even greater than those that have been demonstrated at Aachen. Here's another project. This is from my colleague Zhongchuan Sun, and I was also a partner on this project. And this involves simply intelligently controlling machines without changing anything about the hardware. So it turns out if you look at how operators work, the efficiency of operation is very much less than the optimal. And for example, in this project, we were looking at wheel loaders in a large excavation site. It turns out that the way that the operator actually digs the soil is far less than optimal. And so in this study, we carefully studied how to optimize all the operations on this site. And this leads to two possibilities. One is operator assistance to be more efficient. The other is the possibility to have complete autonomy and more efficient operation resulting. And we've been able to show 20 to 40% improvements in efficiency and also improve productivity. Here's another project. This is a more recent project from Professor Lee, my colleague, Professor Lee. I told you about his energy saving approach. He implemented that energy savings approach on a fully electric track loader shown here. And it has significantly reduced energy consumption and therefore less greenhouse gas impact. Remember, electricity is not necessarily entirely green. It depends on where it comes from. And also, more importantly, even by being more efficient, we can increase the time between rechargings, which is still a big challenge in this kind of equipment. Okay, the last project I'm going to talk about, and I'm going to take a little bit of a deeper dive here, is the most recent project. It's a hybrid powertrain with a renewable fuel engine demonstrated on an agricultural sprayer. So an agricultural sprayer is a good target for energy improvement because it's a very large machine and because it isn't ground engaging. So when you have ground engaging agricultural machines, they're highly dissipative and there's less opportunity for energy saving than there is with something like this large sprayer. Okay, so a little bit about the challenge. Here you can see some members of our research team actually visited Case New Holland, and behind them is the size of you can see the size of the target machine we're working on. So these are large off-road machines with long run times and very hard to decarbonize. Now, here's a few numbers to show why a battery solution is not feasible. So on the existing sprayer, it has a 250 kilowatt engine. They're expected to run for 12 hours without refueling, and sometimes these agricultural sites are quite remote, so refueling is difficult. And for this reason, it has a 150-gallon diesel tank. To have the equivalent amount of energy, if you electrified this machine with lithium-ion batteries, the batteries would weigh 41 metric tons. They'd occupy more than 16,000 liters, and they would cost $1.35 million. So this shows how for heavy equipment, battery solutions are generally not feasible. We have to work on fuels, and that means if we're going to address the climate change issues, they have to be renewable fuels. Okay, here's the um, configuration here for the hydrostatic transmission. So you see you have a single engine, a single pump, various valves for controlling, and four independent variable displacement hydraulic motors on each of the wheels. This is just the main uh, uh, transport part of the machine. Not shown are the auxiliary circuits, the product spray circuit, the braking and steering control circuits, changing the boom and folding the boom for transport between on the road. Okay. Now we've already done an exhaustive software simulation of this system. This was not funded by the government. It was funded by Case New Holland to get some preliminary ideas of um, what could be possible. So you can see the mission profile, the mission profile one graph there that shows roading, which is going at relatively high speed between one field and another. And then you can see going up and down the back and forth on the field spraying. And then there's also intervals of tendering. It takes a lot of liquid to spray these crops. And so you have to have a phase in operation where the vehicle is stationary and you're refilling it with liquid. Okay, so we did a baseline simulation on the existing vehicle, and we carefully separated the information on roading, tendering, accelerating at the beginning of each pass, steady driving within the pass, and then braking at the end of the pass. And we carefully calculated the times, the average power, the average engine fuel consumption, and the hydraulic pump and motor efficiencies in each of these operating conditions. And we could see the following things: that the steady field operation was the largest fraction of the mission, and it had the best engine and pump and motor efficiency. And that's because the machine is designed to operate efficiently in that condition. And then the other conditions, which are less frequent, are it's less it's less desirable. Very poor motor efficiency um, at, while roading. That's because of the low displacement of the motor, which makes it less efficient while going at higher speeds. Tendering, there's significant fuel use in tendering just because the engine is idling. Acceleration had the highest fuel consumption. Braking had a very poor fuel consumption because there's no ability to recover while braking. Okay, so here's how we modified the machine. This is our proposed design to use a biomethane engine. So biomethane is derived from agricultural waste. And by combusting this agricultural waste rather than exhausting it to the atmosphere, we can significantly reduce the greenhouse gas effect. So methane is much worse for the environment than CO2. So even though this emits CO2, because it eliminates emissions of methane, it has a significant negative or decrease in greenhouse gases or improvement of the environment. The other thing is that we're going to put accumulators for energy storage. So we're going to hybridize it. This allows better engine management, also allows recovery of energy during braking for reuse. And for the ancillary circuits, such as the tendering circuit, we're going to electrify them. So what we're going to do is we're going to charge up batteries. And so during the tendering, for example, we can turn the engine off. We can use the electric battery to drive the pumps and significantly reduce fuel consumption. Okay, so here's a little deeper dive. This is the renewable engine. So it's a diesel. We're replacing the diesel with this biomethane engine based on renewable natural gas production. We would actually get this material from a farm. It's called Riverview Dairy in western Minnesota. They have 3 different dairies with 10,000 head of milking cows in each one, and they process 700,000 gallons of manure daily in an anaerobic digester to produce renewable natural gas. And again, as I mentioned before, renewable natural gas prevents release of methane to the atmosphere, and methane is 30 times worse than CO2 when it comes to greenhouse gas effects. The other thing we're going to do is put, as I said, the accumulators here. That decouples the engine power from the wheel power so the engine can operate at more constant and efficient um, um, point. We can regenerate energy um, rather than dissipating with braking into heat. We can add the power from the accumulators to the engine power to increase the acceleration, which improves productivity. We could turn the engine off during tendering, and we have good control of the wheels. So as I mentioned, we have e-pumps, electrical pumps to drive all the auxiliary functions, the liquid product pump, steering, brakes, boom height control, and so on. Now, another thing we're doing is we are changing the tire pressure. So tire pressure is a compromise on these machines. You would like high pressure for on-road operation, and you would like low tire pressure in the field. And so we have implemented a function here where we are going to dynamically change the tire depending on whether we're roading or in the field. Okay, here's our 3-year research proposal. It involves simulation studies, retrofitting a candidate vehicle, and then demonstrating and testing it over a period of 3 years. And here's our project team. It's led by the University of Minnesota. Our partner is Iowa State. They have the large chassis dynamometer, which we don't have, and they have done the tire. They're experts in tires and inflation, and so they would do that. And then we have 4 industry partners. Case New Holland provides the vehicles, Parker, the electrical aspects, Danfoss, the hydraulic aspects and systems aspects, and FPT provides the biomethane engine. So we got a letter from EERE in December 2024 informing us that the hybrid renewal fuel sprayer project was approved for funding for 3 years at $1.8 million. The industry and university partners agreed to provide the required matching funds. Final funding requires the signing of a contract between DOE and the proposing entity, which in this case is the University of Minnesota. Ordinarily, this contract is approved routinely in 30 to 60 days. DOE officials have informed us that they do not have, or they've not been given authority to approve this project. They had no further information. With the closure of EERE, the project will probably never be funded. Okay, so that's the current situation. Let's talk a little longer term. The long-term goal, of course, is to get to net zero carbon. And here are some of the commitments that countries have made to get to net zero carbon. Of course, the commitment doesn't necessarily mean they're going to actually reach it, but at least they're committed to trying. All the countries of the EU have committed to the goal of zero carbon by 2015, as have all these other countries, UK, Norway, New Zealand, and so on. Many of the developed countries of the world have agreed to this 2050 goal. China has agreed to a goal of 2060. And what they said as a country that's more recently developed, they should be given a little more time to realize this goal. I should mention that China is the largest greenhouse gas emitter in the world now. Historically, that position has been held by the US, but it's now held by China. Now, this sort of commitment is very politically sensitive in the United States, but President Biden committed to whoa. Let me see. I just tried to get rid of something, and I've got to. Have you guys seen the screen still?
Yeah, we can see the screen.
Okay. I can't. All right. I tried to get rid of a little title that was there, and all of a sudden this went into very small. Maybe I should stop sharing and reshare or something like that.
Yeah, you could try
fine.
that.
Okay. All right. We're back. All right.
Yeah.
So I said a few years ago, the path to zero carbon is now becoming clear, with major nations making a commitment to achieve zero carbon by 2050. And I would just say recent changes in US policy may delay meeting this goal, unfortunately. Okay, you can get a lot of insight into what is going on by looking at trends in how electricity is generated. And here I'm looking at the different sources of electricity and their projections in the United States. And you can see the gray line is coal. And the use of coal has been declining since about 2005. And by the way, 2005 is when the United States had peak greenhouse emissions. Those emissions have been decreasing ever since, and coal is a major reason, the abandonment of coal. Now, while coal use has declined, natural gas use has increased. And some of this is related to environmental regulations, but the more powerful driver is economics. The fracking revolution has made very large quantities of inexpensive natural gas available in the United States. Now, of course, neither coal nor natural gas is zero carbon emitting, but natural gas has about half of the greenhouse gas emissions of coal. So the switch from coal to natural gas has helped reduce greenhouse gas emissions. Now, the other graphs show non-emitting technologies. You can see nuclear is very flat, and I don't believe there's going to be a major change in the amount of nuclear power in the United States because these plants are so expensive and because they take so long to develop. Although some people are trying to look at new approaches to nuclear, modular approaches. The purple graph is other renewables, and that purple graph is almost entirely hydroelectric power. And hydroelectric power is also not expected to greatly change because of the lack of suitable sites. Most of the most desirable sites have already been used. So the green energy that's increasing now are solar and wind. Solar and wind are the fastest growing and the most economical new sources of energy. And also they don't have any greenhouse gas emissions. So that's a good thing. But over in red, I have some comments. The current administration is doing everything it can to try to prevent replacing fossil fuels with solar and wind. So in March 2024, the US Department of Interior agreed to pay $1 billion to Total Energies, which is a French energy giant, to end their leases for offshore wind projects and instead redirect the company's investment into liquid natural gas production. So that is a bribe to a company with taxpayer money to prevent them from doing renewable energy and instead use fossil fuels. Another of the recent developments in June 2026, that's this month, President Donald Trump announced a $700 million federal investment package to support the struggling U.S. coal industry. So the government is working as hard as it can to try to prevent these needed changes. Okay, now there's a lot of finger pointing between countries, and the data is not really clear, and I think these discussions are mainly unhelpful, but I'm going to engage in them a little bit. So who's responsible for carbon emissions? Okay, let's talk about Chinese steel. So the Chinese have an economy that's based in large part on exports of manufactured products, and one of them is steel. And they use large amounts of coal in their steel manufacturing, and then they sell it to other countries. So there's greenhouse gas emissions associated with that, but should that be on China's account, where the goods are manufactured, or on the final user's account? I think that's unclear, but it might make the Chinese look not as green as they actually are. And here's sort of the opposite effect. Now, Norway is often cited as the greenest country in the world, and there's lots of reasons for that. For one, they're the only country I'm aware that is planning to completely phase out IC engines and have all electric cars. So that sounds very green. But how can Norway do that? Well, there's a couple of factors that Norway has that other countries don't have. One is they're very wealthy, and they're mostly wealthy because of North Sea oil. And so that North Sea oil doesn't count as carbon emissions in Norway. It counts as carbon emissions on whoever the final user is. And the other advantage they have over other countries is they have very plentiful hydroelectricity. So China may not be as may be greener than they seem, and Norway may not be as green as they seem. And then there's the whole issue of wealthy, developing, and poor countries. It's a very complex political situation, and really we've got to all work together. I think it doesn't matter how we talk about who's responsible for what. We all have to work together to get to that goal. Okay, what are net zero energy sources? Well, there's solar, wind, hydro, nuclear, and biomass for renewable electricity, and those are the main potential solutions. There's also a possibility of carbon sequestration, but I'm very, very skeptical of it because it's very expensive, and I think it's mainly an excuse for fossil fuel people to keep doing what they're doing. I don't expect that to be a major part of the solution. There are also many renewable fuels. I've listed some here: methane, ethanol, dimethyl ether, biodiesel, algae, ammonia, and of course hydrogen. Now, some of these are carbon fuels, so you might question whether they're renewable. But if you produce a fuel from a crop and then you regrow the crop the next year, the CO2 emission from that fuel is then absorbed by the crop. And so those can be sustainable practices when you think about the environment. And the other thing is that I'd like to point out is with renewables, such as solar and wind, sometimes they produce more than you need on very windy days or very sunny days. And turning surplus electricity into hydrogen could be one aspect of a good approach. We'll talk a little bit more about hydrogen. like all fuels, it depends on where they come from. These are the color designations. Gray hydrogen is produced from natural gas or coal, so it's not really environmentally friendly at all. Green hydrogen is produced from renewable resources such as wind or solar. Blue hydrogen is produced with carbon capture and sequestration, and pink hydrogen is produced from nuclear power. But if you look at the quantities, almost all the hydrogen we have is either gray or green. The others are smaller, relatively smaller. Now this graph illustrates how hydrogen derived from electricity and renewable energy, wind or solar, can be further utilized. And I'm not going to go into all the detail here. There's many different uses, but I'm just going to look at the first two stages. The first stage is you can use electrolysis to make hydrogen from electricity. The second stage is that you can combine that hydrogen with nitrogen from air to make green ammonia. So a little bit of comment about policy in the United States. The Inflation Reduction Act provides a $3 per kilogram hydrogen production incentive, which is a real game changer because it means that renewable hydrogen is as cheap as hydrogen made from natural gas. Green hydrogen is no longer 10 years away. It's viable right now in the United States. And the Department of Energy in the last administration had what they call an Earthshot goal of $1 for 1 kilogram of clean hydrogen in a decade. And I'll point out that this is very much ongoing. This, in spite of the change of administration, this subsidy is still in effect. So we are hoping that this will help. And many of the states in the United States have gathered together to try and further encourage this hydrogen development. The University of Minnesota has a renewable hydrogen and ammonia pilot plant at our campus in Morris, Minnesota. They take hydrogen and react it with nitrogen to create ammonia, and they've demonstrated it in many agricultural applications. They use it as fertilizer, they use it as fuel, they use it for electricity generation, they use it for grain drying, and so on. So we can take this kind of approach that is being used in agriculture and apply it to commercial off-road vehicles. We can take compressed hydrogen. Now, one of the challenges here is you have to liquefy hydrogen, you have to go to at least 350 atmospheres. So you compress it to 350 to 700 bar. Huge pressures. Or you can use ammonia, and ammonia can be turned into a liquid for as little as 8 atmospheres. Often 8 to 20 atmospheres are used. This is very common, by the way, in agriculture. And so it's much easier to store and transport ammonia than it is hydrogen. And then you use a device called a reformer that then recovers the hydrogen. And then hydrogen can be used two ways. It can be used in a fuel cell to make electricity, or it can be combusted in an engine to make mechanical power. And if it's used in a fuel cell, you'll need a buffer, the battery, to keep the current more or less constant. And then you can electrify all of your actuators, or you can use mechanical shaft power. But in the kinds of machinery we are talking about, the final power actuation is always with hydraulics. You just can't get the power or force density with any other technology. Okay, so here are some of my conclusions. Off-road vehicles consume about 2.4% of the US energy. It's possible to reduce energy to about half. The Department of Energy has invested $37 million in R&D to realize this reduction, but further investment is very much in doubt now. The long-term goal is to achieve net zero carbon for off-road vehicles This requires green fuels such as hydrogen for solar or wind-generated electricity, and hydraulics is expected to play a key role in future off-road vehicle systems. That's because of its superior power and torque density. And with that, I'll conclude. By the way, I have two additional slides. Final shots. Okay, this is basically saying what I've already said. Okay, that just really important to realize that goal of net zero carbon, and it requires cooperation from all the nations of the world. And I also have here appended, and in the interest of time, I won't go over these, but a number of recommended and not recommended references. Okay, so at this point, I'll stop sharing, and I think we have a few minutes for questions, if anybody has any questions.
Thank you very much, Professor Stelson. I have a few questions. One is I was quite taken by the fact that you were using some kind of a common rail system to provide torque. And I encountered it first in the design of diesel injection by Bosch when I was working with them with a common rail system to reduce power generation. That is one. And the second one is there were also attempts at variable compression engines to change IC engines to change the torque that is required, that is to be produced by the engine. I see that you have a variable torque pump. It seems to have a very similar approach to dealing with this problem. So that in the city, you don't need a very high torque engine, so you can use a lower torque and then lower compression, power production, and higher compression when you need higher amount of power, whichever way, city versus highway. Some of those things seem to have appeared in what you are doing, which I thought was quite interesting to me.
Well, I only have a sort of superficial expertise in engines. I have to confess. So
Yeah.
I'm really not going to be able to give a really intelligent comment on that. Except we always have to take a systems approach, and if you have this higher variability in the torque in the engine, that could be one more thing you could manipulate to keep things optimized. Certainly.
That was the thought I was pursuing when I mentioned that.
Yeah, I think it could be investigated. Yeah.
Because I just saw that Mazda is producing a variable compression and torque rotary engine. Anyway, just a thought about that is another dimension which could be available to us with respect to energy consumption.
Yeah, well, these rotary engines have been very played with for many years. They've never quite made it in a big way into the market, but
yes, very much so.
Yeah.
The other thing I was thinking of was, as in the case of aircraft and even in cars, we moved from hydraulic system to fly-by-wire and control-by-wire systems. Is it difficult to do it in off-road engines because the electric motors would not create the kind of torque that is required?
Well, let me clarify that. Boeing produced what they were calling an all-electric airplane. It's not all-electric. So in a conventional airplane, what happens is you have a centralized hydraulic unit, and then you have high-pressure hydraulic oil, which goes through the plane to all the critical flight control surfaces. And what the all-electric, so-called all-electric airplane is you have a central generator, and then you distribute the electricity to small hydraulic units near the actuation. So it's simply not, you don't have the force or the power density with the electrics. And there's another thing that will keep hydraulics in that market, and that is reliability. So in aircraft, people are very conservative, and you can make very easily make these circuits redundant by having two cylinders in parallel. And when they fail, they don't seize, they still move. And so that kind of redundancy makes the aircraft much more reliable, and that's very difficult to realize electrically. So you can see this, by the way, I'll just make another comment. You can see this even on common consumer products. So if you take a log splitter, the most common log splitter has an IC engine, and it drives a hydraulic pump, which drives a cylinder that splits the log. An electric log splitter simply has an electric motor that drives a pump, which drives a cylinder. It does not have a ball screw. For the reason it's really hard to beat a cylinder when it comes to power density and simplicity and cost. So this is the reason, especially with linear actuation, this is the reason hydraulics is not going to go away, I don't believe.
Thank you. Sudhir?
Yeah, thank you, Professor Stelson. So I liked your way of connecting fluid power to the climate change and policy debate. What I wanted to understand was the evolution of different technologies that you have shown. Were they driven by an industry need, or was it coming from a researcher's push or the government's intent in terms of addressing this problem in the off-road vehicles?
Well, okay, I'll talk a little bit about the evolution of our center. In the 2000 timeframe, a number of us at American universities were contacted by the National Fluid Power Association, which is an industry group. And they were frustrated by the fact that there was so few, almost no activity in fluid power in the United States. In contrast with Europe or Asia, where there was a quite active research and education. And the industry was concerned, they simply couldn't find qualified engineers. So that's where this started with us. And so we worked hard to propose an engineering research center, which was very difficult to get. The time we applied, there were 276 proposals that ultimately resulted in 5 centers, and we were one of the 5. And the reason we got it was industry support. So industry was so hungry for this. We had 50 companies supporting the initiative. And so that's how this came about. And then the Engineering Research Center lasted for 10 years, and it was much broader than the off-road vehicles. But we discovered that the off-road vehicles was really a critical need, and we thought to just emphasize that alone and not work in the other areas. That was much more important. And we spent about a 2-year period from 2016 to 2018 seriously lobbying Congress. And it was those industry support that helped us. For example, we would go to the representative from the district in Illinois that contains Peoria. And when we visited their office, they didn't say visitors are coming from the University of Minnesota. They said visitors are coming from Caterpillar. And we would go and visit the office, and we explained to the representative that Caterpillar had 18,000 representative or voters in their district and their families, and industry wants this. That's what propelled it forward. Yeah, that's basically how it worked. And so it was. I flew many times to Washington, I'll tell you, and there were 2 aspects. One was making people in Congress, the Senate and the House, understand the importance of this technology, and most of them were completely ignorant about it. And the other was to educate people in the Department of Energy, who also didn't know as much about it as I expected. In fact, they asked me, that was before that report I showed you, Kim. They asked me how much energy comes from fluid power. What is the Department of Energy asking an individual professor how much energy goes into fluid power? It seems like, and it's because actually Department of Energy spends more time on where the energy comes from than where it goes. But I think that's changing. I think that's changing. Of course, everything is crazy right now. I mean, I meant before there was an increased awareness, and we've proven ourselves in the research projects we've had. We've had results that were consistent with what we said we thought we'd find, and so we've really proven ourselves. That's I don't know if I didn't exactly answer your question, but that's how we did things in the United States.
Mm-hmm.
By the way, we had 7 universities participating in that center.
Yeah. The other question I had was just one more is the how did you end up with this biomethane engine? Is it because you consciously looked at a solution which could work with local resources or some already waste getting generated in a dairy farm, integrating it with the farm? And was there a thinking like that, or how did that come about?
Again, it came from industry. Our partners, Case New Holland, the ownership has changed a lot, but at one point, Fiat owned Case New Holland. FPT stands for Fiat Power Technology. So in sort of the reorganization, that was spun off as a separate company that makes these biomethane engines. And so Case New Holland suggested to us that they would be good industry partners. And we also knew about the effort and the dairy farm and the availability of the biomethane in one of our University of Minnesota locations. So that's how it came about. It's interesting how many of these things come from industry. Maybe the original idea doesn't, but they actually have to welcome it. I mean, in this DOE EERE program, I hope it continues. I don't know about that, but it requires matching funds, which almost inevitably means you must work closely with industry. And they have to supply they have to be significant contributors, let me put it this way, for those kinds of research to be successful.
Thank you.
Are there any questions from the audience? If not, we will close the session as we are already over. Please unmute yourself and go ahead. I suppose, yeah, go ahead. Anything?
No,
Okay.
no, it's me. Yeah.
Thank you, Professor Stelson. And it's been very illuminating for me. And I think also this is important that for someone like Sudhi to understand how many of these projects in the US come together with industry, academic, government cooperation, because this is something that is unfortunately as common in India, because industry is very seldom willing to invest in new technologies. They would rather buy off the shelf from somewhere else. I think this is something from a India point of view. I'm sitting in the US and saying this, but nevertheless, Indian point of view, I think this kind of shift in the way of thinking about bringing new technology has to take place at some point or the other. I don't know when, but I think this is, from that point of view, I really appreciate your lecture, because it will go to hopefully a large number of Indian professors and some industry at least, to think about this problem in a different way than they do today.
If you just permit me to make, I know we're over time, but I'll make just a brief comment. So as you know, I recently retired from the University of Minnesota, and at my retirement event, they gave me a 3-legged stool. The reason is that through my whole time of leading this center, I kept talking about the 3-legged stool. So as you know, a 3-legged stool can only stand if it has 3 strong legs. And the 3 strong legs are government, industry, and universities.
Mm-hmm.
It's the key to getting progress. And if any one of those is missing, it's very difficult. So the government in an enlightened country will invest in long-term R&D because it's good for the country, good for all of humanity for that reason. Industry has to participate because they understand the practical problems and they can really enlighten you. And there's something about having all those young students and all that energy and the combination of research and education that makes universities unique competitors or contributors, I meant to say. And, you know, this was a proven model in the Second World War, which is when really the modern research university was born. And we abandoned this in the United States at our peril. When the vice president of the United States says that universities are the enemy of the people, that shows how far we've strayed from this model, which is the surest way to make progress. So absolutely, India. I mean, India has such a large talent pool. We benefit from it, by the way. I have many colleagues at the University of Minnesota from India, and many of our students also. So, but the United States, if we stop welcoming these people, it's to our own disadvantage for sure.
Thank you very much, and for the lovely lecture and all the insights you have given us. And have a good day. Thank you.
Thank you for inviting me.
Our pleasure.
Okay. Bye-bye.